All right, guys, let's get started. So today what we're going to be talking about is a whole new section. It's going to be separate from the circuits, and it feels kind of weird to me to be leaving circuits already, but we have a few more things to cover and not much time to cover it. So that's the way it's got to be. In terms of what's coming up, we have magnetism, electromagnetism, electromagnetic induction, and electric motors, and then we talk about modern physics.
How many more grades you got left?
Not much.
So none of this has been modern?
Can you have like optional
No.
grades?
No. Huh?
Can you have like optional grades, like if we want to apply after?
No. And the drop grade isn't in yet either. No, and then the bathroom passes aren't either.
Oh yeah, are you gonna do that algorithm thing that you're talking about?
Yeah, we'll figure something out. All right, so magnets. Magnetic fields, guys, are going to operate very similarly to to electric fields. So very similar properties as electric fields. We know as you get farther away from the source of the electric field strength gets weaker. Same thing with magnetism. As you get farther away from the magnet, the magnetic field strength is weaker. And in terms of the strength of the magnetic field, things get a little bit more complicated. So we're not really going to delve into that quite as much. But like electric fields, we have a positive and a negative. With magnets, instead of having a positive and a negative, we'll have a north and south. Okay. So magnets have what we call a north pole and a south pole. When we say pole, I don't mean like geographic pole. What I mean is it's polarized, and so there's a north pole and a south pole. Okay, so a polarized region. And when I say north and south, I don't mean like north and south. That's north. Yeah, north and south. Okay, so in the same way that positive and negative is arbitrary, north and south is really arbitrary as well. Okay. And as y'all know, guys, opposite poles are going to attract. So a north attracts the south, and similar poles or like poles are going to repel. And those forces can be quite substantial. When they were building the first, what are they called? Magnetic. I can't think of what they're called. The devices that they used to separate uranium. You know what those are called? Magnetic centrifuges. Magnetic centrifuges. When they were building those first ones, they made them a little bit too strong, and it pulled the nails out of the wall.
Really?
And
the walls collapsed?
I don't think so. I don't think it pulled all of the nails out of the wall. They probably pulled a few.
I think after the first few, they would
turn it off. Yeah. But right here I have two. I have several permanent magnets that are put together, and just putting the two north of the two south. I don't know which one's which. I mean, it's nearly impossible to get them to touch. You can push as hard as you want to, and they're very, very difficult to get them to.
That was a big part of the presentation. They were trying to put this together. Keys are going everywhere.
Yeah, and I'm going to pass these around and keep it. Okay, these are extremely strong magnets. So I have them turned a certain way. Make sure that you hand them to the next person turned the exact same way, because if they go the other way and they come together, they could pinch you and it would really hurt. Just to kind of give you an example, you see that crack there?
Yeah.
That's where they came together. So it came together and cracked metal. So
flip it over.
So you want to let's see if there's.
Can you pull them apart?
If they don't hurt me, I don't want it.
Let's see. What I'm going to do, guys, you want to see two cracked sides. You want the two cracked sides together. Okay. I'm trying to think that's only Oh, there's another one right there. The two cracked sides that are closest to the end. go together. But just keep them in order, okay? And then extreme and hold them like that. Don't allow them to do that because they'll do weird things. Okay, so hold them.
They'll fling off and break some of his glasses.
You just twist. No, I got this.
O divided by 0.
Alright, so we have really 3 different types of magnets. The first type of magnet we're going to call a permanent magnet. And it's actually a pretty easy definition. A permanent magnet is permanent. Okay, but just to give you the complicated definition, it persistently creates a magnetic field. And what I mean by that, guys, is the magnetic field of a permanent magnet does not get changed by another magnet. Okay, so to give you an example, I'm gonna pull that right back up. Let's say I have a little magnet here, and it's a north here and a south there, and then I put a really strong magnet next to it. Okay, a permanent, well, let's flip that the other way. Okay, so this should want to switch. Okay, a permanent magnet, the polarity of that is not going to switch. What's going to happen is that this is just going to rotate around. Okay, you want to see that? Okay, so here you see the magnet below. Okay, when I take this and I switch it, okay, when I switch it, it just switches. Okay, so that's a permanent magnet. Okay, it doesn't change its polarity. Okay.
Does it have to? Does it depend?
And please do not try that, guys, because these are difficult to separate and even harder to get back together safely. And if they crack, they send little pieces of metal and you don't like it doesn't dry. Okay.
Does it depend on like the thickness
So
of
basically, they're weapons.
Whether it's permanent or not.
What are you asking?
Like you know how like you had it in your hand and you were flipping it. Well, what if it like did it with like a thicker?
Yeah, no. Remember, magnetic fields, like electric fields, depend on distance, and so the farther it gets away, the less force there is. All right, next type of magnet, guys, is called a temporary magnet. Okay. And a temporary magnet is one that, first of all, it easily loses its magnetic field. It also easily picks up a magnetic field.
Stop it. What is it?
Oh, they touched.
Good job, Armand.
Okay.
So a temporary magnet. Your cue for a temporary magnet is if it's attracted to either side of a magnet.
I think you got it stuck. Armand,
I need both of them.
Oh, they like each other.
ask him.
Okay, so here I have a paper clip. Okay, guys, a paper clip is a good example of a temporary magnet. We see the paper clip is attracted to that side, and the paper clip's attracted on that side. Okay, and since the paper clip is becoming a temporary magnet, then we know that the paper clip is a magnet as well. Okay, and if I take this off, okay, since I've magnetized that paper clip, okay, it will temporarily keep those magnetic properties. Okay, however, I had it over on this side. If I take it to this side, okay, then okay, then what? What now?
You didn't switch around with the magnet hang there. I mean the paper clip hang there.
Not indefinitely.
Okay.
Okay,
Because it's temporary.
because it's temporary. Yeah. And I'll talk in a little bit about ways that we can remove those magnetic properties, because you can intentionally remove them. Or not?
He showed you.
Okay.
Like, nah, ain't that easy, man. Ain't that easy.
But it's interesting the way we can demagnetize things. The last type of magnet. Oh, and by the way, guys, both of those temporary magnets and permanent magnets are called ferromagnetic materials. And a ferromagnetic material is anything that has magnetic properties. Right there. Ferromagnetic. All right. A permanent magnet is said to be hard ferromagnetic, whereas a temporary magnet is said to be soft ferromagnetic. When I say soft ferromagnetic, I don't mean you can whack yourself in the head with it and it not hurt. I mean that it doesn't keep its magnetic properties. These.
Oh, yeah, they were right.
Okay, I'm turning it the right way. Okay, so hand them off. No, turn it the way. There we go. Ever so diligently, or carefully, whatever. In that too. Last type, guys, is going to be an electromagnet, and we're going to talk more about electromagnets tomorrow. But electromagnets essentially just turn electric current into magnetism. Okay, so they use the movement of electrons to produce magnetic fields. So anything that's magnetic, anything that's displaying magnetic properties, if we zoomed in on the material, what we would see is that they all have something called magnetic domains. And I mean, you wouldn't see arrows. So what we're allowing these arrows to be is the north side and the south side. Okay.
Which one's north, which one's south?
The tip of the arrow would be, actually I have that backwards. So the tip of the arrow should be south. No. No, that's right. I have it right. Tip of the arrow is north, back of the arrow is south. So this gives us a few interesting properties about magnets. Okay. And by the way, essentially a magnetic domain is just a group of atoms that all have the same magnetic properties. Okay? And so something is said to be magnetized if all the magnetic domains line up. Okay? So that gives us some interesting properties, and one of those interesting properties is, let's say I have a magnet, and I take that magnet and I cut it in half. Okay, I have a north side over here and a south side over here. Right? Okay, but when I take it and divide it in half, now I have a north and a south, and a north and a south. Okay, and the reason for that is because of these magnetic domains. And so if we look at, kind of zoom in on here, we said the tip of an arrow means north. Okay, so if I take this and I cut it in half right here. Oh, no. Stop it. Yeah, so if I take this and I cut it in half right here, okay, what we would see, guys, is one side, the arrows are pointing toward the line. Okay, so on this side, I get the norths, and on this side, I get the back of the arrow or the south. So that's the reason why we always have a north and a south. Okay, the reason why this side is the strongest of the norths is because that's where all the arrows end. And there's the reason why this is the strongest of the south is that's where all the arrows begin. I have nothing but arrow ends there, and I have nothing but arrow tips here. But in this middle region, I have both arrow ends and arrow tips. I mean, there's no arrows, but you get what I'm saying, right? You're asking a really deep question that we're going to get to eventually. And by eventually, I mean right now. So if something is not magnetized, okay, then what that means, guys, is that the magnetic domains are not aligned. Okay, so in a paper clip, that is sitting unmagnetized. Okay, I know since it's unmagnetized that the magnetic domains are just squabbled in random order. Okay, however, when I put a magnet up to it, it takes all the magnetic domains and lines them up. Okay, so that's what creates the magnetism in a temporary magnet. And can you kind of think over time, with a temporary magnet, those magnetic domains over time start to shift, and that's the reason why a temporary magnet loses its magnetism. And I think actually, yeah, that's on the next slide. Getting ahead of myself. Make sense? And we can actually, if we look with a microscope, we can see these little magnetic domains. Okay, so we do know that they're there.
So it wasn't that slide. So it wasn't that slide.
Metals generally like stick together, but like if you get my shirt up to that, I don't know. Does everything have those arrows in
Magnetism?
it? Yeah.
No.
Okay. So
Okay.
like
Oh boy.
So, in permanent magnets, guys, those domains are said to be kind of locked in place. Okay, and really there's a fine line between hard ferromagnetic and soft ferromagnetic. I mean, it's not like this is absolutely hard ferromagnetic and this is absolutely soft ferromagnetic. So because you can have hard iron or soft iron. So it depends on the material a little bit. But one thing that influences it is there's a certain temperature. And as you raise temperature, what happens to atoms? They start to move around. Okay, so as the temperature raises, magnetic domains start to shift around. That makes sense?
Which means you turn it into temporary magnet.
Okay, so one way to make a temporary magnet lose its magnetism is by heating it up. Okay, because when you heat it up, that takes the things and it jostles them around. Okay, another way to jostle them around is to actually just jostle them around. Just tap it on something, hit it, drop it. Okay, a temporary magnet can lose its magnetism just by being dropped. Mm-hmm.
So does that mean that you can change a permanent magnet to a temporary magnet by heating it up? Or permanent magnets are always going to be permanent magnets?
Okay, a permanent magnet, when you heat it up, the magnetic domains would be more flexible, and so that's how you get it to align in one direction. So if you heated it up enough, then you could get it to realign.
Oh.
And then when it cools back down, it's set. Okay, so for this right here, I'm going to take these two and turn them into temporary magnets. I'll get that in a second. Okay, so right now they're temporary magnets. If I pull them apart, put them back together, then they are, well, not anymore. It's sticking to my fingers.
Your fingers become temporary magnets.
wait, can we become?
Yeah.
No.
What?
Well, then why does it stick to your
Magneto.
fingers?
No.
So Superman.
Because my hands are clammy.
It's nasty.
All right, so there. So it's still a temporary magnet, right? Okay, if I take these, okay, jostle around those magnetic domains. Okay, what we should see, guys, okay, is no more magnetism there. Okay.
What if you like make it hold a little like a better magnet?
It wouldn't be a better magnet, but the magnetic domains would be harder to.
I thought you just handed them the paper clips like that.
Yeah, no. Have fun with these. All right, so question, guys. You've earned it. So question. Why are many metallic objects attracted to magnets when they're not being magnets? I mean, like this paper clip right here is not a magnet right now, but if I put it up to that magnet, it's attracted.
Arrows in it.
So,
It wants to move to an area
Huh?
of magnetism.
It's
to an
for
area of
a
magnetism.
magnetic.
so,
Maybe Because that makes
But
it
if,
hard.
but I mean, but magnetic forces only happen between two magnetic objects. That's the reason why a magnetic force does not affect you, because you're not magnetic. So why are metals often attracted?
Metals are magnetic.
It wouldn't be magnetized.
What happens? What do you think happens to the magnetic domains in a metal when you put it up to a magnet? They line up. Okay, so when you put a metal up to a magnet, it makes the metal a magnet. So it's attracted to the magnet. And the same way that, remember when if I put some negative charge up to a neutral object, it induced charge because electrons fleed. Okay, same idea.
Except you can make that magnet not a magnet. After you make a metal object a magnet, you can make it an unmagnet.
You can demagnetize it.
So then how do they prevent, do they just make it a really, really hard magnet, and that's how they keep, like...
Well, that's why we have hard ferromagnetic materials and soft ferromagnetic materials. And a hard ferromagnetic material is one that at room temperature, it's not going to adjust magnetic domains. But soft ferromagnetic materials, okay. So I have a piece of aluminum up here. Aluminum, is it magnetic? Okay, so if it's not magnetic, it's said to be paramagnetic. Ferromagnetic means it is magnetic. Paramagnetic means it's not magnetic. Okay, so what we see here, guys, absolutely no attraction to that aluminum. Okay, why is there no attraction to the aluminum? Okay, it doesn't have magnetic domains. Okay,
But
so
metals do. What?
most metals do, but aluminum does not. It has to do with unpaired electrons. The more unpaired electrons it has in the valence, the stronger its magnetism is. And I'm just counting on y'all to have learned about unpaired electrons in chemistry, because
No.
Is it just the electrons are about
I'm not sure
themselves?
if they even know.
I mean, electrons come in pairs, right? Typically.
Yeah.
Yeah.
Wait.
Did y'all remember? Y'all did that in chemistry. Y'all did the whole thing with boxes, and you had like
Yeah, there's a up and a down.
yeah. Okay. The more of these that are unpaired, the more magnetic it is. Okay. Aluminum only has one that's unpaired. Iron has like 4 that's unpaired. Okay. So that makes iron more magnetic. And the reason behind that is complicated, and we'll get there eventually. Okay, so magnetic fields. In an electric field, the electric field runs from the blank end to the blank end. Positive to negative. It runs from positive to negative, right? Okay. In magnetic fields, it's going to run from north to south. Okay. So when I draw in the magnetic field lines, which we're not really going to spend any time doing that. But if I were to draw in the magnetic field lines, then my arrows would need to point toward the south end. So since arrows are pointing toward the south end, that tells me, guys, that those arrows represent the force on the north pole of a magnet. Okay, so the arrow of the magnetic field line represents the force on north. We good? So far? Sure? Good? Did everybody get to play with the magnets? Y'all are so lively today. Huh? Yes, you did. Okay, so one of the more famous magnetic fields is the Earth's magnetic field. We should all be very thankful that we have it. The Earth has a pretty strong magnetic field surrounding it. And it actually extends many...
And that's why they're cracked.
and it extends many hundreds of miles around the Earth. We call that the magnetosphere, that region around the Earth that's magnetized, or that's inside of the magnetic field. And that magnetic field provides protection from the sun. And the way that it does that, guys, is the sun will occasionally burst out charged particles that we call solar flare. Okay. And those charged particles move very rapidly, and since they move very rapidly, if the Earth had no magnetic field, and those would come and they would smash into the Earth's atmosphere, right? In some way that an asteroid smashes into the Earth's atmosphere. And if those particles hit the particles of the atmosphere just right, kind of envision in your mind almost like a pool cue hitting the billiard balls. Okay? I mean, things scatter out, right? Okay, so if enough solar wind came by, what we would see is our atmosphere would start to deplete. Okay? And in fact, that's what happened to Mars. That's the reason why Mars has a very thin atmosphere, because it doesn't have a very strong magnetic field. Okay, so the way that the Earth's magnetic field protects us is when these charged particles come in, they get deflected around the Earth because of that magnetic field. Okay, so it's almost like a barrier around the Earth. Okay, however, if there's a really strong solar flare, okay, what can happen is there can be a collapse of the magnetic field around the back. Okay, and if that magnetic field collapses around the back, those charged particles get directed to the poles. Okay, and when they get directed to the poles, it creates the northern and southern lights. Okay, so that's how the northern and southern lights are created. When those charged particles smash into the atmospheric atoms get excited, and excited atoms typically do what? They glow. Okay, they give off photons. Okay, so what you're seeing is those solar flares smashing into the atmosphere and exciting the particles.
So then, are there certain times that you can, like certain times of the year that you can go see them, and they happen more often during that times, or is it really just completely random?
Well, but our year is not necessarily the sun. I mean, we don't really know the sun's cycle. I mean, the sun's cycle might not be an Earth calendar year.
So then, how do people?
It's probably just better viewing conditions in certain parts of the year because of that part of the Earth.
Well, the atmosphere is different in different. I mean, obviously during the winter, the nights are a little bit longer, and so you have a better chance of seeing things in the winter because the night's longer.
But you can't like plan.
Yeah, you can't really like plan and say, okay, the lights will be here on this day.
They actually have there's predictors. You can go.
That's what I was asking.
There's like a website that says at 8:45 and at 10:17, and these are the highlights of the day.
I can't even.
Wait, so this happens on regular
But how far can they predict?
days? Is that not?
Not with any great accuracy.
Probably like the
That's
same.
a serial.
Yeah.
It's gonna be sunny all week.
I mean, I would think that it probably comes down to light travels faster than those charged particles, and so we see that there's about to be some charged particles. You know, I don't know how accurate. I'm not familiar with all that. The Earth's magnetic field, guys. By the way, other planets have the same thing. Saturn, we have observed the southern lights on Saturn as well. I think I have a picture of that. It's like, hey, in your free time, guys, look up a picture of Saturn's.
I ain't got free time.
What is this free time?
Okay. So, just to make things extra confusing, if we let the Earth be a big magnet, then the magnetic north would be located at the South Pole. I didn't make that decision. It was up to me. But it's going to make sense in a second why. Okay? Well, not why it's located at the south, but why we call the north and all that kind of stuff. And compasses, guys, are created by just allowing a little magnet to spin. And on a magnet, we have a north side and we have a south side. No. Okay, so here, guys, I have a little compass.
Because the north
thought that was a diameter.
is
Why would you want to have a compass that small?
Okay. So I have a little compass there, guys. The blue end is the north, and that little pointy thing is just a magnet. Okay, it's a magnet that can freely rotate. So the blue end is the north end of that magnet, and that might be backwards. That might be the south. Whatever.
It says so.
And so, yeah, I think, well, the magnetic fields in here are kind of weird, but I'm thinking the silver is probably the north end.
Probably because of your
I-
supermagnet.
Oh my gosh, it just moved. The poles just changed.
Moves close blue, it's moving closer.
What are y'all
It's
talking?
guiding us to treasure that's following.
He got a magnet. Like,
Everybody click.
Guys, it's not, guys, we have a lot of stuff to cover. We don't have time to play.
he got
So, if this, guys, if this is the north end of a magnet, and this is the south end of a magnet, and I put another magnet up to it, then the north end should point away from a north, and it should point toward a south, right? So if this is the north end, it's going to tell me which end of a magnet I'm looking at. Okay, so when I put this magnet up to it, okay, what we see is the north end is pointing away now. So this tells me that this is the north end of this magnet. Okay, when I flip this, okay, we see it reverse. Okay, when I flip this, guys, we see it. Can y'all? We see it reverse. Okay, so now the north end is pointing toward this end, so that tells me that that's the south end. Okay, and as I rotate it, what we should see is that compass just aligning itself to the magnetic field of that magnet. Okay, so for the Earth,
That's why the magnetic north is so cool.
and evidently this is not a very good magnet because now it's pointing the other way.
Maybe you charged it. You charged it.
It must have been a temporary magnet. And we'll talk about the implications of that. Well, no. No. And I magnetized my pen too, so it's. So if this, essentially, all you got to do is you just say, if I know which end of a magnet is the north end, then the north end should point to the geographic north of the Earth because that's the magnetic south. Okay, so the north end of a magnet points north because it's pointing toward the magnetic south
Away from the magnetic north.
and away from yes. Make sense? Okay. However, things get a little weird here because the Earth's magnetic north is not really located at the north. It's actually located a little bit off north. And so if I have the Earth here and say this is the axis of rotation, then the magnetic field is actually a little bit off. Okay, and so the result of that is that the closer you get north, the less accurate a compass is. Because think, if you're right here, north should be in this direction, right? I mean, if we rotated the Earth, right, it would be up. But since we're looking at the Earth from the side, it'd be at an angle, right? Okay. However, what you're going to see is the compass is going to point that way, because it's going to point toward the magnetic north. And to make things even worse, that moves, so it's not even predictable. It might move 25 miles, or it might move 50 miles.
Wait, how does it move?
Okay, well, there's not a big magnet in the middle of the Earth that just sits there. There's not a big magnet in the middle of the Earth that just sits there. And it's not like a giant brought a big magnet and magnetized the Earth. So there's got to be something creating that magnetic field. It's not just a persistent magnetic field. And that magnetic field is created by the churning and turning of the Earth's molten core. Okay, so as the Earth's molten core is turning, that's generating a magnetic field. Okay, so the theory with Mars is a large asteroid came and struck Mars, and you can actually see a huge crater from it. And when that happened, it disrupted the molten core, and so that messed up the magnetic field.
Does the molten core just not like turn anymore? Is the planet like dead? I guess.
I don't think it has a molten core anymore.
So it's just a solid piece of rock.
So-
I'm not all that informed on it, and I don't know how informed we are on it. I mean, we've never been to the center of the Earth, much less the center of Mars. So, I'm not that informed on it. But there is evidence that the Earth's magnetic field has switched before, and so obviously that would just be caused by, instead of rotating that way, it rotates the other way. Okay, and it's like every. I like how the worst implication you can come up with is you're walking around with a compass and it's telling you the wrong direction. Man. But obviously that's not good when it switches. I want to say it switches something like every 200,000 years or something like that. It goes in. It's cyclical. But I think we're overdue for a switching. But
So it might switch like anything.
huh?
So it might switch like
I mean, it's not just like bam, switch, reboot. I mean,
all of our compasses, or does it switch back?
no. What would happen is this churning would slow down and then start churning in the other way.
So how does that happen?
I have no idea.
So what? How do we know that does happen?
Huh?
How do we know that does happen?
There are little particles in soil that will align themselves to the magnetic field. And so what we can do is we can dig down and we can see for a while they're pointing this way. 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 And so you can estimate.
You can predict like
And so now it's
You can-
time for that to happen.
I've heard that a really long time ago, and it's been a long time since I've heard that. And so I don't want to say
So
yes, it is.
a huge earthquake or something.
I don't know. I'm not. You start talking about geology, you really start to get out of my field of study. Okay, we have one more thing I wanted to talk about. All right, compasses, guys, do not point toward the pole of a magnet. Okay, I had to go along with it. I didn't want to get ahead of it. What they do is they align themselves to a magnetic field. So there's some interesting implications of that. And what that means, guys, is, can I switch back to the, okay, what that means is if I put a magnet right here, it would point in that direction. And if I mean a compass, if I put a compass right here, it would point in that direction. And a compass right here would point in that direction. Okay, they're all just going to point with the magnetic field. Okay, so looking at this compass here, okay, what we should see is notice how it's not pointing toward the north or south pole. It's just aligning itself with the magnetic field. And as I take this magnet and move it, okay, what you should see is it's aligning itself with those curves of the magnetic field. Does that make sense? Okay, and the reason why is because right here, if I were to draw out the magnetic field around this thing, and hopefully I don't get my pen stuck to it, okay, we would see something like that. Okay, so as this moves along this path, and I did a bad job drawing it, obviously, okay, what we should see, guys, is that should point just right along that path. And you can see I did a crummy job drawing it, but you get the picture. Okay? All right, we have some other things we're supposed to talk about, but I think, oh, we have a talk it out to do. Grab, yeah, yay!
Wait, I thought we had more stuff to talk about.
I guess we don't. All right, guys, talk it out. We'll talk about it later. Oh,
Okay, we're done.
I didn't tell it to do that. This is so slow. I'm going to turn the recorder off.